It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with the experiment, it's wrong. Richard Feynman. Hello, everyone. Probably see videos later on tonight. Maybe. We'll see. But let's get right to it, shall we? Gravity. Do you guys know what gravity is? Because I don't think you know what gravity is. I don't think anyone knows what gravity is, because I don't even think the scientists really know what gravity is. You ask someone who what gravity is, they'll probably give you the Newtonian law of universal gravity. Is that what is this? Gravitation. Sorry. You know what that is? Well, if you look it up, as you will, because you don't want to be wrong, so you're gonna Google it. And first thing you have is NASA, spaceplace.nasa.gov, which is an interesting one, because if you go there, it's what is gravity? And I was pointing this out earlier today on gosh, what's his name? Nathan Oakley's debate stuff. I attended it a little bit earlier today. So they say it's the force by which a planet or other body draws objects toward the center. The force of gravity keeps all the planets in orbit around the sun. Pretty simple, because this is for kids, pretty much. And it's NASA. Now, however, if you go to Wikipedia, you know, they're going to give you a couple of things, right? They're going to say, hey, it's a natural phenomenon by which all things with mass or energy, including planets, stars, galaxies, even light, are brought toward or gravitate toward another. Now, and of course, on Earth, gravity gives weight to physical objects, and the moon's gravity causes the ocean's tides. We'll get more into that later. Now, it says on the second paragraph, gravity is most accurately described by the general theory of relativity, proposed by Albert Einstein in 1915, which describes gravity not as a force, but as a consequence of the curvature of space-time caused by the uneven distribution of mass. Now, however, for most applications, gravity is well approximated by Newton's law of universal gravitation, which describes gravity as a force. Which causes any two bodies to be attached to each other with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Pretty similar to Coulomb's law, which is based on energy. So here we go. Tell me, people. I mean, you guys think I'm probably nuts. So is gravity not as a force, or is gravity as a force? Just tell me, which one is it? Is it Newtonian law? Is it Einstein's theory? I mean, you tell me, because then we can go from there. Hold on, I think daughter's saying goodnight. Hold on. Hi. How was it? Did you get it? Did you win? I got it. Come in. Come here. You won something in bingo?
It was like the last game.
The last one? That's pretty lucky.
I wanted a book so bad.
You wanted a book so bad. Alright, it's you can say hi to this camera. So you won Have You Seen My Cat by Eric Carl. Are you excited? Did you get to say bingo? Did you jump up and go bingo? Yeah? Was it fun? Alright, that's good. Oh.
Time for go to bed.
Alright, time to go to bed. It's late. Good night.
What are you doing?
Live streaming.
So what are you doing?
So I just talk and try to explain things to people. Eventually you're gonna watch videos too. Yeah, I know.
Come on, Sylvia.
Alright,
Let's go.
good night. Alright, sorry for that segue. She'll be watching this when she's older. She might laugh. That'd be good. Okay, let's finish this up. Alright, so, alright, gravity. Is it a force or is it not a force? I mean, whoever you're going to be arguing against, against flat Earth, and you're going to use gravity. You're going to have to define gravity, and there's plenty of definitions of what gravity is. So, you know, again, you're going to have to choose a theory, either Newton's theory or Einstein's theory. And then we'll go from there. But there you go. You're going to have to choose a theory. What is gravity? Now, before I get into all the details, you can look into the details. You need to look into the details. One of the series I'm creating is, look, the waking up process is when you research for yourself. You can't have anyone research for you. You can't. The whole reason why you're asleep is because you let other people do the research for you. When you do the research yourself, you'll find that, hey, it doesn't make sense. Why are we just believing all this one person? They're just telling us everything, showing us nothing. Okay, here we go. So what's interesting about this is something I never knew until today. That NASA, it says gravity is important to us. We cannot live on Earth without it. The sun's gravity keeps Earth in orbit around it, keeping us at a comfortable distance to enjoy the sun's light and warmth. It holds down our atmosphere and the air we need to breathe. Gravity is what holds our world together. However, gravity isn't the same everywhere on Earth. I repeat, NASA. Gravity isn't the same everywhere on Earth. Gravity is slightly stronger over places with more mass underground than over places with less mass. NASA uses 2 spacecraft to measure these variations in Earth's gravity. These spacecraft are part of the Gravity Recovery and Climate Experiment, GRACE mission. The GRACE mission helps scientists to create maps of gravity variations on Earth. Areas in blue have slightly weaker gravity, and areas in red have slightly stronger gravity. This image is credited to the NASA University of Texas Center for Space Research. GRACE detects tiny changes in gravity over time. These changes have revealed important details about our planet. For example, GRACE monitors changes in sea level and can detect changes in Earth's crust brought on by earthquakes. This was last updated, this article, on May 4th, 2017. So, what would be interesting if they actually did an experiment? Get the reddest area that you can find, which has slightly stronger gravity. Go to the bluest area that you can find, which has the weakest gravity. And as you can see, it looks like the sea levels, I don't know why certain sea levels are much weaker, but you just go to those areas, weaker gravity, and you have those red ones, stronger gravity. So you could probably weigh yourself. Just bring a scale, go to those areas, get on sea level, weigh yourself in the blue area, weigh yourself in the, I guess a neutral level would be what, yellow, and then weigh yourself in the red area. There should be a difference in weight, right? You can also run a lot of experiments that way. You don't see it, they're just telling you stuff. I never heard about this before. Isn't that interesting? Gravity is a force, is an effect, not a force. It's a farce. Now, the Earth, they say that the moon is what causes tidal changes every 6 hours. You would think it'd be every 24 hours. But then, of course, they say the sun has some force towards it too. So here we go. So the solar eclipse, the great thing about solar eclipses is you've got the sun and you got the moon in line in front of it. That's what they say. And therefore, you know what? If you're observing that phenomena, that part of the world, the tides should be at the highest point, right? The highest point. Any other time, any other day, right before it or right after it, it should be lower than the highest tide of that time of the solar eclipse. It's just logical thinking right there. So if that's also the case, and you're on the other side of the world, and the low tide should be at its lowest at that time, where people are observing from one side of the globe. There's the highest of the high tides should be. Other side of the world, it should be lowest of low tides. Now, if you want to actually look into it, and here's the solar eclipse of August 21, 2017, dubbed the Great American Eclipse, because you could see the total solar eclipse within a band that spanned the entire contiguous United States, from the Pacific to the Atlantic. So, what's great about tide charts, some of the tide charts, and I look for it. A lot of it, they don't keep those tide charts. I tried looking for it. It's pretty tough, but I found it. And this one is in Falmouth. This is just all in the UK. tidetimes.org.uk. And August 27th, or August 21st in 2017. Now this is not quite. It's like the midway. It's like a quarter, right, of the distance between the near side and the halfway point of the globe. So it should be, I don't know, it's not a good test, but I'll move it towards Seattle, Washington, and so the antipode, there's an antipodes map. So if you're in Seattle, Washington, the exact opposite side of the globe is supposedly somewhere near South Africa and Madagascar. There's these islands there, but I doubt there's tide charts there. So let's go to Seattle, Puget Sound. That was from there, right? This is on August 20th and gives you a 4-day forecast of tides, 20th, 21st, 22nd, 23rd. So on the 21st, and if you look on the solar eclipse, you'll know that eclipse starts beginning at 10:16 at PDT, and let's see, and it ends at around 2:44. So if that be around, let's see, oh, that's going UTC. Oh, okay, never mind. I got it. So let's go and see how it is in the morning and the daytime. So on the 21st at 4:25, you got 11-foot high tide. In Seattle, it should be the highest of the high tides. Should be on the 21st. Should be the highest, and then later on that night, 6:13 p.m., 11.7 feet high tide. Yet the next day, you got slightly lower, 0.1 at 5:18 a.m. And then at what's really weird is the low tide got really low. But it should, like, the low tide shouldn't be as low. So you could do the high and the low. So the low tide shouldn't be as low as the other days. And it does kind of make sense here because of that. But the high tides, it's almost exactly the same as the other day's high tides. It's actually slightly less. Like the day of the solar eclipse, total solar eclipse, 11.7 feet high. The 22nd, the next day, 11.8. The day after, even 11.8. So that's just a little bit surprising. I would think, it shouldn't be as high of a tide on those other days. It's not like there's another total eclipse happening the next day. And like the low tide is actually higher. So it doesn't, the low tide is actually lower than these days, which during the eclipse it shouldn't be. Interesting stuff. No one will look into it. Someone has to look into it, and that's what people do. We all look into it. and we share what we look into so other people could look into it as well. Maybe I'm wrong. Maybe someone finds something better to measure, to track these metrics and whatnot. So, okay, Madagascar, we're looking at the low tide. Should be the lowest of the low tide because it's pretty much at the other side of the world at the same time. Okay, so at the low tide, it's on that day, it's 0.69. And at night, around 10:20 p.m. Eastern, it's 0.54. So that should be the lowest of the low. Yet then when we look at the next day, it's 0.4 low, or 0.54 low, which is exact same as the previous night, and then 0.43, which is actually lower than any of those. It should have been as low as this during the actual eclipse time on the 21st, but that didn't happen. I mean, on the 21st, the lowest that you get for low tide, and it seems to be just 1. It's just 0.69. And really late, then it's 0.54 actually. Yeah. Sometimes I can't see. I don't like this chart. I wouldn't use this chart if I was going fishing in the saltwater, but this is the only one that has data left. All the other, a lot of the other tidal charts, they just get rid of their tide charts. Don't know why. This one I like. It seems a little bit more accurate. For example, this is during the solar eclipse, right? But this is in the UK. You would still think that it would affect the tides on the 20th. So the highest is 5.3, the lowest is 0.53. So if we go to the 20th, the day before, the highest 5.13 and 0.82 is low tide. And we go to the day after the eclipse, the highest is 5.4, the lowest is 0.31. It seems like there's really not much of a drastic difference between those days. It's just kind of almost like an average increase, decrease. So that's just food for thought. And I actually picked another point. I think it's Morgan's Point in Texas, in case you do want to look at it in Seattle. And of course, you're going to find the same thing. It's what's weird is you would think that it would affect any part of the ocean. The bay might be just different than just the Puget Sound. They're very similar, anyways, my opinion. But still, it's quite different than in Seattle Puget Sound. I mean, you've got a high tide of 11.7 feet, but I guess moon's gravity really didn't affect the Galveston Bay very much. The highest high tide was 1.3 feet. Galveston. Things are weird in Texas. Okay. So, what's interesting about gravity and space is the whole thing about what they have with space, and NASA points it out, and you know what? So does CERN. Like, if you go to home.cern science, so interstellar space, MBAR, and so it says a vacuum is empty as interstellar space. Okay. So what they're saying is, to avoid colliding with gas molecules inside the accelerator, the beams of particles in a Large Hadron Collider must travel in a vacuum as empty as interstellar space. So they're able to create something similar so they can run their experiments. The largest vacuum system in the world is what they say. Now, what's fun is that, like I keep saying, if I was up in space, man, I'd be doing so many experiments. I mean, if I was in an interstellar space station, I wouldn't be playing like tricks of just gravity, like blue, 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 blue. Hey, look at me. I'm just kind of going, woo. I'd be running real experiments. I mean, this is like, if you're in space, it's a vacuum. They say it's a vacuum. They don't tell you exactly when that vacuum happens and why. They say gravity prevents. They say gravity prevents our the stuff in our atmosphere, the air, the water, from being sucked into the vastness of this huge vacuum of space. Gravity is one of the weakest forces. They'll even say it. Look, it says, gravity is the weakest of the 4 fundamental forces of physics, approximately 10 to 38 times weaker than the strong force, 10 to 36 times weaker than the electromagnetic force, and there's a force called the weak force. It's 10 to 29 times weaker than the weak force. That's how weak they say gravity is. And we think this gravity is a huge big thing. I think the latest thing is that I heard recently is gravity is faster than light. I think that's one of the latest things out there, because the idea is if the sun disappeared, what would happen first? Because what do you hear? You hear the light that reaches from the light from the sun. It takes 15 minutes to get to Earth. That's because of the vast distance of the sun to the Earth. Well, the sun disappeared. It just left. It disappeared. It got destroyed. What would happen? Would we not see it after 15 minutes and things would just continually get cold, or the big gravitation, the gravitational force between the sun and all the planets, that disappears? So do we just slingshot to the next nearest biggest body, I guess, within space? We would know that because we'd be like, whatever gravitational pull, whatever, just slingshot us to something else. Or would just, our speed wouldn't decrease if we're in a vacuum. It would just increase. So we'd find something else that go whoosh, faster. We'd accelerate. Interesting stuff. That's what I used to think. But not anymore. It's just the dumbest thing if you think about it. Now, what I like, I scuba dive. I've always wanted to scuba dive more, get my own equipment. I've only really rented equipment for scuba diving. One of the things that I've always wanted to do was scuba dive on a mountain lake. I mean, the water is going to be, and the creatures within there might be different than the waters of sea level and also below sea level and anywhere else. And so what it is so they just say at sea level you begin with 1 bar at the surface. So when you go down about 33 feet, you're going to be at 2 bars of pressure because it's just the density of water. Now, the density of water doesn't change whether you're at sea level, below sea level, or above sea level. The density of water stays the same. So if you're a mile above the surface, instead of being at 1 bar of pressure, you're at 0.8 bars of pressure. But if you go down 33 feet, you're not at, say, if you go down 33 feet, you're at 1.8 bars. So you're still at 33 feet, you still have 1 bar differential. However, because it is going from, wait, that doesn't make sense. I think this is wrong. Because if you start at 0.8 and you're going down to 1.8, oh, I see. It's not 1.6. Yeah, okay, so it's 1.8. It's an increase of 125% pressure differential when you're a mile up as opposed to just sea level. Isn't that weird? You would think it would be the same, but it's not. So the higher you go, the higher up in elevation you go, the less pressure there is, yet the pressure differential becomes higher. That's just a weird thing, isn't it? It really is an anomaly towards gravity. The other thing is, why is the pressure being so much lower? The atmospheric pressure lower the higher you go up. I mean, isn't that closer to the vacuum? I mean, one, nature abhors a vacuum. Name one instance where there's a natural vacuum. Just something in nature where there's just a vacuum. I doubt you'll find anything. There's no vacuum in nature. That's why you hear the quote, nature abhors a vacuum. And I think that's what Niels Bohr. I may have been getting it wrong. But I don't know why I know so many quotes. I think that's why I don't know. Okay. So the higher you go, the closer you get to the vacuum, somehow it switches. The gravity is just not strong enough, and boom, things would go. You're now in a vacuum. I mean, that doesn't quite make sense. But, and of course, is gravity a force or is it not a force? Is it because of the curve of the space-time? Like, all you have to do is really think about it. And it's not simple. People want a simple explanation of gravity. People want a simple explanation of a vacuum in space. And here's another thing, like I segued, sorry. You can boil water in space where if it is a vacuum, it would boil. It would start boiling, and then it would pretty much turn into a solid ice. So, like at room temperature, I mean, the less pressure there is, it's going to take less heat to boil water. So if you're up in the mountains, you don't need 212 degrees Fahrenheit or 100 degrees Celsius to boil water. It's going to take less. So that's just one thing that you can keep in mind. Now, so that's the thing. If you're what would be just interesting as hell is to just jettison just some water, not just directly, just like spitting it out. Have like a big balloon of water that you can like time to just explode and see what happens to the water. I mean, somehow just try to make it so when that water, when it hits that vacuum, whatever it is, just see what happens. I mean, there's just so many things. You can just do a straight spray of water. You can just do whole like water balloons full of water, just and pop them or something, and just see what happens in space in the vacuum. That's just so much cool stuff you can do. Yet we only see those experiments on Earth. You never see NASA do it. What the hell are they doing up there? They're playing around in the Interstellar Space Station, doing little flips and whatnot. But again, you guys who think Flat Earth and there's preposterous that you don't think there's a vacuum in space. And you can't explain it. You can't explain anything. Because if you can explain it, and if you can actually prove gravity, you would be the next Einstein. You would be more famous than Einstein. You would be more famous than Newton. You'd be more famous than Einstein. You'd be more famous than Newton. All you have to do is pretty much have a better theory or just prove within an experiment how the Newton's theory where gravity is a force, or show the curve of space-time to show that gravity is not a force, and that you would be the scientist of the century. You would not even the century, of like a millennia. I don't even know what is a millennia. Is that 1,000 years? Yeah, okay. So a millennia. But no one's gonna be that, because it's pretty preposterous, really, if you think about it. But everyone somehow knows gravity is real and vacuum in space is real. It doesn't make sense at all in any way, shape or form. Because first, you can't even define gravity. You can't. Because no, they define gravity for you. So NASA says this Newtonian gravity. Except there's times where it's not. I like it. And they won't ever show anything. I mean, look, this is like, find something like this. Just find it. Spend some time. You're not gonna. I mean, if you're watching my videos are just kind of dry, boring, long. 31. You spent 31 minutes watching me. Go spend 31 minutes doing your own research on any of these things. And I'm afraid for you because you're gonna end up like me. You don't want to end up like me. That's why you won't do the research. And you're saying, Ebon, your research is faulty. Blah 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 blah. Fine. Just listen to other people. Just whatever they tell you. They tell you, oh, here's another thing. And I'm gonna probably present this in one of my series. Here we go. Let's see. All right. Quick one. See the red square and the blue square? One of these squares is bigger than the other. Which one is it? Is it the blue square that's bigger than the red square, or is it the red square bigger than the blue square? Well, you know what? I lied. These squares are exactly the same. And you had to guess. You're saying, blue one's bigger than the red one. No, red one's bigger than the blue one. I formulated what was going to be in your mind, something where your observations are already influenced by what I just told you, and what I just told you was a lie. So that's anything and anyone. They can tell you what you directly observe. It'll contradict what you directly observe and what you think, and they'll already tell you that it's wrong. And one of these that they choose for you is right. They do this all the time. So don't trust anybody. Do your own research. That's what everyone says in the truther community. If, anyone who's waking up to the lies of this world. And if you don't think I was telling the truth, well, here we go. This is just how I created it. And you can see that it's just, there's no little breaks. There's no little curves like in the globe earth. It's all straight lines. And you can see that they're all equal. So, yeah. One is not bigger than the other. I was lying. I was just illustrating a point. Okay. That's it. Now, you might see me later. I'm going to play Age of Empires with my brother. I might live stream it so you can watch me play games. Real-time strategy game, which I haven't played. I've been playing for fun, so that's what it is. You're not going to see some groundbreaking new strategy or anything like that. I'm just going to have fun. All right. Thank you very much, and I will see you guys later tonight.